Today's lesson is on finding rational roots. So we're going to be looking for roots of equations that happen to be rational numbers. So the major objective is to determine the rational roots of any polynomial function with integral coefficients, so integer value coefficients, and attempt to identify any remaining irrational or imaginary roots. First of all, the rational root theorem says the following. If a function with integral coefficients is given by the following: f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus ... a bunch of other terms plus some constant at the end. So if we're given some random function here, then any rational root of the function will be given by plus or minus p over q, where p is an integral factor of a0, meaning it's a factor of whatever this is. So this is like 8. P could be 4, 2, 1, negative 4, negative 2, negative 1. It could be 8, it could be negative 8. Any of the factors of this, that's what P is. And Q is an integral factor of a sub n, the leading coefficient. So remember, Q is the leading coefficients factors, and P is the constant terms factors. So whatever the factors of this are, or whatever the factors of this are all of the possibilities we could have for a rational root. Now there's going to be many of those possibilities, but they're not always going to end up becoming our roots for those specific problems. So example 1 asks to verify that the roots of the following equation satisfy the rational root theorem. So we take a look at this. We're going to see first of all right away, here's our standard equation, and I'm giving you the factored form. Okay? So first, from this we could see that our roots are going to be x equals 4, x equals 2/3, and x equals negative 5/4. How do we get those? We solve each of those when set equal to 0. So look at those. Well, 4 is really 4 over 1. 2/3 is 2/3, and negative 5/4 is negative 5/4. But we have to take a look at our values. So we said that the numerator has to be a factor of this quantity, and the denominator needs to be a factor of this quantity. Well, the factors of 12 are going to be 1, 2, 3, 4, 6, and 12. And those can be plus or minus. The factors of 40 are much further, or much more. We're going to have 1, 2, 4, 5, 8, 10, 20, and 40. And again, these are also all plus or minus. These are all plus or minus. So we've got a lot of possible factors for some of our numbers here. Well, take a look real quick. Here's the factors of the Q value. Well, 1 appears right there. 3 appears right there. 4 appears right there. Down here now, the factors of 40 are going to be apparent on numerators. Oh, here's 4, there's 4. 2 is there, and negative 5 is right there. Remember, 5 could be plus or minus for these ones. So all of our values, or all of our factors that are listed here, out of all of them, some of them do appear in the roots of this equation. So here's a general approach to finding roots of a given polynomial function. Step 1, list the possible rational roots. And that's what we were just doing a minute ago. We're talking about all the values of p and q. And we'll do an example in a minute where we're going to actually sit there and list all of the possible p and q values. Second step says to use the graphing calculator to determine which of the possible roots may, in fact, be roots. So students should use their graphing calculator here. Step 3 is to use synthetic division to show that the number is indeed a root, and eventually reduce the equation down to a second-degree polynomial using the depressed equations. Step 4 is saying to use the quadratic formula, or factoring, to determine the final 2 roots of this. So those are going to be the 4 steps we're going to use to approach this. Let's go through an example using all 4 of these steps as guidelines. So the example says, using the rational root theorem, determine with evidence the locations of the zeros of the following function. Now, it is extremely useful to be able to use your calculator for step 2, so we should think to do that. Now, what we're going to notice is that for this problem we have to start by listing all of the possible rational roots. Well, if we want to find the zeros of this function, we set it equal to 0. So let's set this equal to 0 now. And let's list all the p's and q's. Well, take a look. The factors of 10 are going to be 1, 2, 5, and 10, all positive or negative. So those are the numerators you can have. Factors of q are going to be 1, 2, 3, and 6, plus or minus. So we have to think about all the possibilities of any of these values over any of these, which is a lot. So let's start with 10 as our numerator and put it over all 4 of these. So we could have 10 over 6, 10 over 3, 10 over 2, and 10 over 1. Again, plus or minus for all of these quantities, always. Then go next with the 5. We could have 5 over 6, 5 over 3, but you know what? It looks to me that 5 over 3 already appears here. 10 over 6 is 5 over 3. So what I can do is I could say to myself, well, you know what? Let me get rid of the form of it that's not simplified. This one at the top was not simplified. Let me get rid of it now, because I've got 5 over 3 now. Next comes 5 over 2. And then finally we have 5 over 1. But again, 5 over 1 already appears. It's right there. Get rid of the non-reduced form. So we have so far 6 possible answers using the 10 and using the 5 as our p-values. We're using all 4 of these q's every time. Next we have to try the 2. So we could start with 2 over 6. Then we could have 2 over 3. Then we could have 2 over 2. And finally 2 over 1. Well, 2 over 2, let's see if that shows up anywhere. Does that show up anywhere? 2 over 2 is the same as 1 over 1, but I don't see that anywhere, so we're good. 2 over 1 would be like having 10 over 5, but that doesn't show up anywhere, and 5 over 2.5, so that's good. 2/3, is that a new one? Let's take a look. 2/3 is indeed new. None of these repeat as 2/3 is simplified form. And 2/6 is really 1/3. So 1/3 is appearing there, but we don't have that anywhere else. So let's keep going. The last option now. Try 1 as the numerator. 1/6, 1/3, 1/2, 1 over 1. Alright, now we have some repeaters. Let's take a look here. 1/6, not repeating anywhere else. 1/3 is, though. 2/6 and 1/3 are the same. So we get rid of this 2/6. Then we have 1/2. Does 1/2 show up anywhere? Let's see. No 1/2 here, no 1/2 here, we're good. But then 1 over 1 appears right there as 2 over 2. So let's get rid of the 2 over 2. So in the end of the day, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 options. 12 possible options, which to me, to be honest, is just too many. So, step 2 told us, use the graphing calculator to determine which of these possible roots may in fact be a root. Well, take a look. Looks like this is going somewhere between 0 and -1. Here's 1. Here's 2. It looks like this one's going right through 2 right here. And this one's going through around like 2.5 or so. Okay, between 2 and 3. So let's choose 2 to try. So let's try 2 in this synthetic table to see if 2 is a root. And remember, if 2 is a root, the remainder will indeed be 0. So we're going to try 2 in our original equation. Remembering the original equation, its coefficients will end up being 6, -25, 21, and 10. Because, again, it was 6x cubed minus 25x squared plus 21x plus 10. Bring down the 6 to start. 2 times 6 is 12. 12 plus -25 is -13. 2 times -13 is -26. -26 and 21 is -5. 2 times -5 is -10. -10 plus 10 is 0. So because this is 0, yes, this is a root. Now, since we have one of the roots, we can look at our depressed equation. Our depressed equation becomes 6x squared minus 13x minus 5. So because the depressed equation is actually quadratic, we can go ahead and solve this either by factoring a quadratic formula. I would personally factor it. Factoring it becomes 3x plus 1 and 2x minus 5. Now remember, we're trying to find the roots of the original equation, So when we get this suppressed equation, we can just find its roots to help us. So this is going to become x equals negative 1/3, or x equals 5/2. And if you check, both of these answers do appear in our original list of possible roots. Okay, so we have those two answers as roots. What was our other root? Our other root was right here, 2. So we have 3 roots. The roots are 2, negative 1/3, and 5/2. Okay? Checking that we see them up here. 2 appears right here. Negative 1/3, here's the negative 1/3. And the positive 5/2 is the positive 5/2. Okay? All of our answers do appear as options. Let's take a look at a second. Example 3 says, if the velocity in feet per second of a particle defined on the interval from 0 to 5 seconds is given by the function v of t equals 16 to the 4th minus 41t cubed plus 105t squared minus 113t plus 35. Determine when the particle is at rest. So we want to think to ourselves first. When a particle is at rest, it means it's not moving. So its velocity must be equal to 0. So what we can do is start by setting the velocity function equal to 0. And we can clearly see that when we set a function equal to 0, we're trying to find the zeros of that function, or the roots of the resulting equation. So we have a long list here, because we have to list all the possible factors of this over all the possible factors of this. Well, this can be, okay, those 4 values with plus or minuses, and 6 we already did last time. It's 1, 2, 3, or 6. So our possible values already are going to be 35 over 6, 35 over 3, 35 over 2, 35 over 1. All of which I don't think are going to get repeated. After 35, we have to do 7. 7 over 6, 7 over 3, 7 over 2, 7 over 1. None of those are repeats of the previous part. Then we've got our 5. 5 over 6, 5 over 3, 5 over 2, and 5 over 1. And lastly, what we have to do here is take a look at the last possibilities, which are the 1s. So plus or minus 1 over 6, 1 over 3, 1 over 2, and 1 over 1. And we have to take a look at all 16 of these and see if any of them repeat themselves. If they do, we don't have to consider them as possible roots. Doesn't look like right away any of these repeat themselves. Now, what we want to look at next is back at our graph and say on our graph, well, there looks like there's a root between 0 and 1, and another one between 2 and 3. Well, let's circle in red the ones that appear between 0 and 1. So 1/2 is there, a 1/3 is there, and a 1/6 is there. Everything else is bigger than 1. Which of these fractions we'll circle in blue? So this was the red root. And in blue, we'll look for things that are between the numbers 2 and 3. Well, as a reduced fraction, none of these are between 2 and 3. None of these, let's see, actually. 7 over 3 is between 2 and 3. This is between 3 and 4. No, no. 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 Yes. No. So the ones that we circled in blue are the possible numbers that could be this value, and the ones in red are the possible numbers that could be this value. So this is a tough one. We have to think about where they lie. It looks like the red one is about halfway, so I would try 1/2 in my table. So let's go ahead and make a synthetic table using the possible root of 1/2. Okay, so to do that, we've got our coefficients along the top. Remember, it was 6t to the 4th minus 41t cubed plus 105t squared minus 113t plus 35. And we are testing 1/2. Bring down the 6. Half of 6 is 3. 3 minus 41 is negative 38. Half of negative 38 is negative 19. Negative 19 and 105 is going to give us 86. Half of 86 is going to be 43. 43 and negative 113 is negative 70. Half of that is negative 35, plus 35 is 0. So this is indeed one of our roots. From that, let's bring down our depressed equation here. Setting this depressed equation equal to 0, we'll see that we have another synthetic table to try out. Another one. So now we need to go back and take a look and realize, alright, we found 1/2. So we found the root that was highlighted in red. So we can get rid of those ones. Those choices are out now. What choices do we have left for the other root? Well, the other root was right here between 2 and 3. It's either 5/2 or it's 7/3. It's one or the other. I'm going to choose 7/3 because I know it's going to work. You can try 5/2 and you won't get 0 as your remainder, so you'll know that 5/2 doesn't work, so then you can try 7/3. But you have to actually show that it works. Because just because 5/2 doesn't work does not necessarily mean that 7/3 is going to work. The root that's here could be irrational and thus not show up in this list. So we have to actually go ahead and check. So I'm going to check 7/3 in this new reduced table. So plugging in 7/3 and running it through this table is going to be 6, negative 38, 86, and negative 70. So bringing down the 6, 7/3 times 6 minus 38 is going to give us negative 24. Okay, because that's going to give you 14 there. And 7/3 times 24 is going to give you a negative 56. Negative 56 and 80 is going to give 30. 7/3 times 30 is 70. 70 plus negative 70 is 0. So because this is 0, because the remainders are zeros, that's what makes these two the roots. So we have 2 roots now. That's only 2 of them. But this was t to the 4th power. So we have to think about the fact that we still have 2 more. Well, here's our reduced equation, or our depressed equation even further. So let's go ahead and write what we have now. And it's t, not x. Not that it matters, obviously. And we set the depressed equation equal to 0 again. Now for this example, what we're going to notice is that this does not factor. So to solve this one, we have to use the quadratic formula. And what we're going to get as a result of the quadratic formula is simply going to be 2 plus or minus I. And notice they are imaginary. They come in pairs, as we said already. They come in pairs. So this was originally t to the 4th. And what we'll notice is that we have, let's move this guy down, we have 1 root, a 2nd root, a 3rd root, and a 4th root, because that's a pair of them. So we have 4 different values, or 4 different roots of that equation. So again, this problem says determine when the particle is at rest. The particle is at rest during this time, or at this time, and at this time. Well, this time really doesn't matter. So for the sake of our problem, we can get rid of it, because the time of the particle cannot be at rest during the imaginary times. Okay? But again, the other 2 roots that are imaginary, they still show up as roots of the equation, but there's only 2 real solutions to this problem, and they are 1/2 second and 7/3 second. So example 4 here is very similar to the last few, where it's telling us to solve the following equation. We're going to use our rational root theorem to find some possible roots, but the first thing to notice is that everything in this problem is either a decimal that has a half in it, or it's a fraction with a half in it. So it looks to me like we should multiply by 2. So if we double everything, it'll help us here. So we're going to start by doubling everything in this equation. So we're going to end up with getting 2x cubed plus 3x squared minus 14x. And if we double this, we're going to get minus 21 equals 0. So this beginning here is a 2x cubed. Now, when we look at this part now, it looks a little bit easier, because now we can look at our p's and q's and figure out what our integers are. Well, the factors of this are going to be 21, 1, or 7 and 3. So we have 4 possible p values. The q values, we have just 1 or 2. So, for this kind of a problem, we have to think to ourselves, let's list all the possible p's over q's. So let's list our p's over q's. So we start by listing the p values. Let's try 21 over 2, or 21 over 1. Then the second possibility goes to 7. So we could have 7 over 2, or 7 over 1. After that, we could have 3 over 2, or 3 over 1. Again, what are we doing? We're going one at a time. 21 over either of these. 7 over either of these. 3 over either of these. And then finally 1 over either of these. And the 1 part is going to give me 1 over 2, or 1 over 1. Okay? So let's take a look to see if we have any repeated factors. 21 halves and 20 over 1 by themselves. 7 halves, 7 over 1. Those don't repeat. 3 halves and 3, 1 half and 1. Nothing repeats itself, so there's no need to cancel. But we have a lot of options here. But if we look at our graph of this now, we can see that there's probably a root around 1, 2, 2.5. Another one around -1, -1.5, right? So we got one around 2.5, one around -1.5. And this is around like -2 and change. So we've got some options here. It looks to me like this right here seems to split it exactly. So this is around -1.5, and that's right here. Right? 3 halves is 1.5, so we use the negative part for that. So let's test -3 halves first. So again, choosing our test subject is sometimes the toughest part. So we'll start with -3 halves to test. We have to put this into our function. So we have 2, 3, -14, -21. Bring it down to 2. -3 halves times 2. Well, that's just going to give me a 0 there. And that -3 halves times 0 is 0, plus -14 is -14. -3 halves of -14 is 21. And 21 plus -21 is 0. So this is indeed a root, because the remainder is 0. So this indicates that it is a root, okay, because the remainder is 0. So the root is boxed in over here. Here's the root. The evidence is right here. Okay, this is the evidence right here. Now, with that given fact, we started with a cubic, so the depressed equation must be quadratic now. So the depressed equation looks like this. Well, we could solve this. We don't need to go any further. There's no need to test anymore or go to another table, because this is quadratic in nature. So set this equal to 0 so that we can find the roots of this one. To find the roots here, let's add 14. We get 2x squared equals 14. Divided by 2, we get x squared equals 7. So what are we going to end up getting here? We're going to get plus or minus root 7. And it's not as obvious right away, because this was not one of our choices from our list. Well, you might ask, why wasn't it one of the choices? Take a look. The list is the list of possible rational roots. This is clearly irrational, but its value as a decimal is around 2.7. Okay, 2.65, but around 2.7. So what we could really do is take a look here and say, well, it does make sense, right? 1, 2, around 2.7. 1, 2, around -2.7. So this is the square root 7 as a root. This is negative square root 7 as a root. This is the -3 halves as a root that was right here. So this part, or this problem said solve the equation, so we solved the equation. We got answers of 3 halves, -3 halves, -root 7, and positive root 7. Those are our 3 possible roots. Again, only the -3 halves is the rational root.